let's talk this chapter 12, guys. Really nice. Talks about panels. So I'm going to grab a couple of pictures, just talk about the pictures, and then I'll highlight what's in the PowerPoint presentation. If you're dealing with a single phase panel, oops. If you're dealing with single phase panel, what happened to my? Okay, so that's what I'm going to go, guys. Panel board selection and installation. But I'm going to go directly into a couple of nice looking pictures, like I said. If you're dealing with single phase panel, we're done with single phase panel. I want you guys please to understand the following. From right to left, you're going to have phase A, phase B, or hot 1, hot 2. On the right side is going to be the neutral. On the left side is going to be the ground. Can I have thumbs up, Chad? You open this panel right now, you're going to have from left to right the phases A, B, and C, if any, and the neutral is going to be on the left. The ground is going to be on the right. If it's a service panel, they always bond the neutral to the ground. Can you guys see that here? They grab it and bond it together. Can I have thumbs up? We understand only at the service you have main bonding jumper. Main bonding jumper only at the service. Can I have thumbs up, Chad? That's it. You're looking at a panel. The second thing I want to highlight for this panel is, can you guys see how it goes odds on the left, even on the right? Everybody can see these are all the odd numbers here, all the even numbers. If you graduate from Dunwoody not knowing that these are how the panel boards are listed, we cheated you, right? On the right side, it will be on the right, even odd. The second thing, can you guys see that the ones opposite to each other are on phase A. The ones underneath them immediately are on phase B. Can you guys see that? Everybody can see that? Every two circuit breakers opposite to each other are on the same phase. Thumbs up, Chad. We understand? Opposite. Every two circuit breakers next to each other are on phase A and B. Right? That's how you get to 240. Everybody understand this? Please don't graduate from here not knowing this. That's what I want to highlight. Everybody understand that? So we have a neutral, we have a phase, and we have hot 1, hot 2. Then I'm going to jump directly into 3-phase. I think the second one is 3-phase because we are in the 3-phase business. So this is for single-phase panels. We don't use single-phase panels a lot in this project. Here's your 3-phase panel. Does that look familiar to you guys? Phase A, phase B, phase C. Neutral, ground. Now, if this is a main panel, let's just do it main panel. This is my, let's put a circuit breaker, oops. Let's put a circuit breaker here, guys, and make it my main panel. Right on the spot here, Chad. Circuit breaker, and circuit breaker, and circuit breaker here. And this is my 500 amp main panel. This is my main panel. Now, Jeff, since it's a main panel, I want to go bond what? The neutral to where? To the ground. This is my main bonding jumper, and I want to take the ground to where? To Mother Earth. Can I have thumbs up, Chad? This is how you do it in a main panel. One more time. Phase A, phase B, phase C, neutral, ground. This is how when you open it. If I want a 3-phase load, if I need a 3-phase load, so here's my air handling unit. Air handling unit. So I want to go with the following. I want to color code them. I have my black, and I have my blue, and I have my red. Do I need a neutral for that one? No. If I need a lighting circuit, let's say a lighting circuit. Here's a light. So I need to take it from this circuit, black. And what do I need? A neutral. Where's my neutral? Let's use a neutral, this one. And I need a neutral. How am I going to get the neutral there? Neutral. Can I have thumbs up, Chat? We fully understand this. That's what I want you guys to understand. Please. So phase A, B, C, ground, neutral. I need also to take a ground. Here's my ground here. And also you always take a ground to the equipment. That's how you circuit in the panel. That's what you guys did with me in Revit. You did with me in CAD. From left to right, ABC, neutral, ground. Thumbs up, Chad. Top to bottom. The odds are on the left, evens on the right. Any adjacent two circuit breakers are coming from two different phases. Cool? Any opposite circuit breakers are coming from the same phase. Please don't graduate from here not knowing that this is how panels are. Can I have thumbs up, Chad, one more time? Cool. Okay, so that's what I want to emphasize here. So that's my panel. We talked about this, so let's go. That's my panel. Now, oops, wow, what did I do here? Oh, gee. Did you do that for me? Okay, so let's go back here. I think I went too far on that. There you go. Andrew, I can't thank you enough for that little and push it, man. That makes my life easier. Okay, here's another panel. Can you guys see how they take two circuit breakers, 7 and 9? That's 2 hots, 208, 2 hots, 208. This is how do you take 3-phase, 12, 14, and 16 3-phase, 13, 15, and 17 3-phase. Can you guys see how they circuit out of these? That's exactly what you guys done with your friend Chad. Exactly what you've done with your friend Chad. Can I have thumbs up, Chad? Cool. The second thing I want to emphasize here, if you have a building with 2 different voltages, by code, Jeff, you have to identify the branch circuits and the feeders. If you have a building with 2 different voltages, so here's a panel. This panel, I have to identify it as 208/120 volt 3-phase panel. Right next to it here, I have 480/277 3-phase panel. This panel is 400 amp. This panel, let's just say it was 200 amp. Okay. If you have, see, the building has 2 voltages. By code, you have to put a label right at the top of the panel that identify the voltage of the panel, the amp of the panel. You also have to have the interrupting rating. So 65 kilo amp. This one is 22 kilo amp, right? The last thing that you need to identify by code, which people don't understand, the color code of the wiring system. The color code of the wiring system. So right here, you're going to do the following: phase A, phase B, phase C, color code. Color code for the wiring. This is going to be black. This will be red. This will be blue. You go right here on the face of that panel, color code. You're going to have the phase A is going to be brown. Phase B is going to be orange. And phase C is going to be what? Yellow. Industry standard. And the last thing, guys, is neutral. It's going to be gray here. And neutral from this one is going to be white. This is required by code. If you have a panel, if you have 2 panels, have different voltages, you have to put the color code of the wiring system for the branch circuits and the feeders. Can I have thumbs up? That's the most misunderstood concept. In the building that we have, Darren, do we have 2 voltages? We only have 208, 120. By the way, 208, 120 is 1 voltage system. When I say 2 voltages, 3-phase voltages, like 480, 208. We have only 1 voltage. Do I need to color code on the panels? Very good idea, but I don't need to. So, Joe, when you pull a branch circuit from this panel, what color, single phase, what color the conductor's branch circuit or feeder has to be? Brown, orange, or yellow, and gray. If you pull a branch circuit or feeder out of this panel, what color code the conductor's branch circuit or feeder has to be? Blue, red, black, red, or blue. Thumbs up, Chad. We fully understand that one. The last thing you're going to put right on these panels is arc flash. You need to have a label. These are all labels. You're going to have an arc flash warning. Same thing here. You're going to have arc flash warning. Okay? And the last thing, did they say the last thing before? The last thing so you see all these are labels on the panels. All these are labels. The last thing you need to do, you need to label the panel based on 2011, label it with the feeder that feeds the panel. So let's go with red. Feeder fed from, let's call this one, I'm going to call this panel, guys, what do you want to call this panel? Let's call it MP. MP. This is LP, fed from MP. So this panel is actually fed from here. Okay. Then this panel, you're going to write on it fed from, where do you want to feed this one? Fed from XFR, from a transformer. Right? Can you guys see that? You have to have a label right stamped at the panel that said this panel is fed from which panel? That's 2011.
Can you do a 480 control?
Via a transformer. Typically, will be this one would be actually the other way around. Would be if this is fed from, this would be probably more realistically from XFR1. This is XFR. This one will be fed from via transformer. Will be fed from which panels now? Let's call this is main panel. I want to call this is MP. This will be say P1. Panel 1, this is fed from MP. Oops. Okay, that's more like it. Can I have thumbs up, Chad? We understand the labels for panels. You graduate from here, you don't know the labels, you're doomed. Color code for the conductors, piece of cake, right? Okay, so moving on into another topic that I want to emphasize here as when they design panels, guys, they have a couple of things when they design panels. Here's how they design a panel. From top to bottom, phase A, phase B, phase A, B, C. If you go from right to left, A, B, C, A, B, C. Side, A, B, C. Right, can you see that? A, B, C, A, B, C. From top, backward here, A, B, C. So with the way they designed the phases, from left to right, ABC. Front to back, ABC. Top to bottom, ABC. Can I have thumbs up, Chad? Be aware, that's how the phases are located. Who cares? Because if you flip two phases, what happened to the air handling unit? Blowing air in the other direction. Okay? That's very important to know the design of them. This is called wild leg. You guys, this is 2.8. This system is so-called 240. Oops. Be aware that this can be used in a commercial, in certain commercial buildings. This system is called 480. Oops, not 480, Chad. 240. This system is 240/120 3-phase. This is the only way you can get 240 120 3-phase. The one and only way. This is called the center tap delta. Can you guys see where they take the delta here, the center tab it? This is called the wild leg. Remember that wild bastard leg, whatever, high phase leg? The voltage between here and the neutral, anybody remember? 208 volt. So that's why they call it wild leg. And you can only feed from phase A, and this is phase A, let's just say phase A, phase B, phase C. So you're going to find phase A, phase B, phase C. So this is very important, guys. When you go into a panel and you find phase A and empty, this one is empty here, and phase A, B, C, and then A, B, again, this one is empty. This is an indication that this is a center dab delta with a wild leg. Because if you take phase B to the neutral, if you dare to take this one and take the neutral, where's my neutral, to it, you have 208 volt. If this is rated for 120, what have you done to this load? Can I see here the word burn it? So this is another system not commonly used that you have, that you get you to it. This system you have to warn it. Phase B has 208 volt to ground. You have to have a label on it. So the electricians and apprentices, when they walk here, they say, hey, dumber than a rock, don't take anything from phase B into the neutral. You can't believe how many people burn a lot of equipment, guys, from this system. You hear the stories all the time. The electrician walked in here. Oops, here's a slot for a 20 amp circuit. Plug it in and feed your lights, and bam, 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 burn all your lights. Can I have thumbs up? We understand this special system. Where would you use a system like this? Personally, well houses for cities, lift stations for cities are notoriously famous of having them. In a place, I always tell people, in a place where 10% is single phase load and 90% three phase load. A place where single phase is only 10% of your load, that could be an application, and the system is 240. If the system is other than 240, I wouldn't even think about that thing, right? I wouldn't even think about it. If it's 208, it doesn't come in 208. Only if you need 243 phase that you use this system. Can I have thumbs up, Chad? We fully understand that. Okay, so that's a special system, the wild leg. When we have panels, guys, a couple of pictures here for you. Really nice pictures. When we have panels, we can have a feeder. This is the poor man's work. You grab a feeder, 400 amp feeder, and you tie, can you see that? And you tag it. You tab these feeder. Well, I'm not going to talk about the tab rules. Inside a gutter or a box, these are junction boxes. Can you see that? And you tab them within the 10 foot tab and 25 feet tab, not 10 feet away. And then you got 300 amps, three 200 amp panels out of them. Three 200 amp panels out of them. Okay? I want you to remember, guys, when we size panels, the overcurrent protection device cannot be overcurrent protection device must be equal or less than panel size. You guys remember that? So if this is a 200 amp panel, this is a 225 amp panel, right? Can I put a 400 amp circuit breaker ahead of it? No. Can I put 200 amp ahead of it? Yes. For panels, there's the size of the cover inside it and the size of the circuit breaker ahead of it or in it. The size of the copper have to match the size of the overcurrent protection device or be more. Can you guys see that? The fuses are 120. The copper is 225. Is this okay for the fuse to be less than the copper? Yes. Is the other way around, right? Meaning, can I have a 225 amp fuse supporting or protecting a 200 amp panel? No. Can I have a thumbs up, Chad? We fully understand that. That's it. So that's a couple of things, way of doing panels. This is the poor man's way. What would the rich man's way be? Rich man's way is to put another panel here and feed these directly from this third panel. So that will be my main panel. Right? What's the problem with this? What's the problem with this? You're spending more money. Okay? Okay, so that's what I want to highlight in this slide, guys. My slide here. Okay, so feeders, we talk about the tab at a different time. Panels. When you have a panel, you can have the overcurrent protection device inside the panel. Can you guys see that? This is a 225 amp panel. This is called main logs only. Can you guys see that? Do you remember the main logs only? Why do they call it main logs only? Because the overcurrent protection device is where? Ahead of it, somewhere else. Somewhere else. Now, Darren, I don't know how many of you guys know that. Probably you because you're journeymen. Anybody tell me what's the advantage of doing it this way versus putting it right in here, 150? I need somebody to tell me what is the advantage. It has to do with safety. What's the advantage of putting it here versus putting it here? Yes. Okay, that's a good point. Well, first of all, if I put it here, do I still need another one here? Yes, because you still need to protect the feeder. Two things. Number one, if you put 150, if you bring that fuse here, you still have to have another fuse here to protect the feeder. So by putting it here, you saved yourself what? A fuse or a circuit breaker. That's why main logs are only, people love them. Another advantage, guys, of putting the circuit breaker here, arc flash. If you have an arc flash right in this panel, the fuse is protecting you from the arc flash. If you put the fuse right in here, the arc flash have to be based on ahead of the fuse, based on the rating ahead of the fuse. That's another advantage of having the fuse outside. So this is called main lugs only. If you put it inside, it becomes main circuit breaker. Can I have, do you guys understand? You use them in Revit, right? Main lugs only, main circuit breaker. Main circuit breaker, it has a main in it. Main lugs only, it does not have a main in it. Any comments, any questions? Which one is the cheaper? No main in it. Which one is better in terms of design? No main on it too. Okay. So that's basically the circuit breaker. Here's the second option. Can you guys see that? The second option is to have two circuit breakers. In this case, I have 200 amps, 200 amps. Each one of these 200 amps. Fusible panel. So I have 200 amp here and 200 amp here. So what's the problem with this? I have to pay. I pay for another expensive, right? Expensive. You have to have a. I could have gotten away. This is main fuse. Main fuse. This is right. There's a main fuse in it. It's not main lugs only. When we size the fuses or circuit breaker, guys, remember that 80% continuous load. I cannot rate a fuse or a circuit breaker more than 80% of its size. For example, if this fuse was 100 amp, can somebody tell me what's the largest continuous load they can pull out of this? You got it. Unless the circuit breaker is rated for 100% circuit breakers, which they only make them become viable if you are probably 600 amps or higher. Even 1,000 amps, it makes sense to put them 100% rated circuit breaker. You guys see that 100% rated circuit breaker right here? This is, you're talking about 1,000 amp or higher. So for example, if I have a 4,000 amp, how much current continuously can I get out of 4,000 amp? And 4,000 amp, I will remind you, is 100% rated. How much current can I get out of this boy? It's Friday, man. 4,000. Can I have thumbs up, Chad? We fully understand what 100% rated fuse is or circuit breaker. And it becomes viable if your circuit breaker or fuse is what? More than 1,000. If you haven't dealt with more than 1,000, you probably haven't dealt with it. When Jerry Stanson came here and he was talking about these drought circuit breakers, that's what we're talking about. These are 100% rated circuit breakers. Okay, so that's what I want to highlight. The other one, guys, I want to highlight. I'm just going through the picture here. You can feed circuit breakers. This is not feed through subfeed. This is called subfeed. You guys remember when Jerry was here and he talked about subfeed? This is your subfeed. You have 400 amp and you feed 200 amp here and you feed another 200 amp here. Subfeed. So you bring the feeder. Can you guys see? They bring the feeder here, and then after you bring the feeder to the disconnect, you tab the feeder and you come back and you feed another panel. And you're moving inside the panel. What's the advantage of this? The advantage is you're moving from, you have two tops. Where would you use something like this if you ran out of receptacles, out of receptacle circuits, and you need more switches, circuit breakers? That's a good application. You have a lighting panel and you ran out of 84 lights in it. That's a good application, guys, to feed subfeeding. Can I have thumbs up, guys, about subfeeding? What's the issue with? Then you need a gutter. Can you guys see that gutter space here? You need more space here so you can pull the feeders through it. Can I have thumbs up about subfeed? That's my subfeed. The last part, guys, talks about clearances. Any question about the panels? So for panels, the overcome protection device can be inside them or outside. It has to be equal to the panel size or less. You have to label them with arc flash, interrupting rating, full load amp, voltage, and what did we say? a short circuit, and the feed that feeds them, and the labels, the conductor size. Let me go directly into a couple of things about working spaces. Okay. I don't know if I have working spaces. Okay. All right. The second thing I'm going to highlight, guys, about panels is working space. When you work in the front of panels, you have to work safely and egress safely the working space of a panel. The code requires to have a depth of a working space equivalent to the following. If your voltage is 0 to ground, this is phase to ground, If your voltage to ground is between 0 and 150, you have to have 3 feet clearances in front of it, right? If it's minimum, for condition 1. Condition 1 is sheetrock wall. Here's condition 1. Here's condition 1 right here. Sheetrock wall. I'm a panel in the front of the sheetrock wall. Ungrounded object 3 feet. If your system is between these two values, it's also 3 feet. Any question, guys, about clearances in the front of panels? Clearances in front of panels are there for people to work on the equipment, right? So here's a panel like this. This is my panel. This is 120, 208 panel. So 120, right in the front of it. How much do I need? 3 feet. Why? Because in the front of it, is there any grounded objects? There's no any grounded objects all the way back. So at least 3 feet. If that panel was 208, 48277, then I still need 2 feet. Can I have everybody understand what condition 1? Sheetrock wall, right there. Sheetrock wall. Look at condition 2. When you go to condition 2, guys, really nice. That's what I like about these pictures, because it's better than everything. When you go to condition 2, now condition 2, grounded parts. Here's a grounded part. This block wall is a grounded part. So if you have a panel and in the front of it is a grounded part. So if suppose that this panel, this wall is here, grounded, right? So can you guys see the distance? If it's 208, this is for my 208 system and my 240 system. This one is for 480 system, right? For 240, 208 system, I still need 3. For the 480, what do I need? They added how many? Extra what? Half a foot. Can I have thumbs up, Chad? That's it. That's for the grounded. I want to remind you guys, the one before it, here's what the one before it was. If you don't have a grounded, 3, 3, both of them, right? Now, if you go back here, you have 4, you added half. Now, the last one, if you have 2 panels facing each other, can you guys see that? 2 panels facing each other. Make sense? Same thing. 240, 208, 3 feet, continue to be 3. 480 jumps into what? 4 feet. Can I have thumbs up, Chad? We fully understand the clearances in front of the panels. That's why a lot of engineers, Kerry, when you have your panel, the first thing they do, they draw a 4-foot box in the front of the panel, and they say clearances, just 4, regardless of. Just start with 4. So if it's 3, you're covered, and if it's 3, you're covered, and if it's 4, you're covered. Cool? So if this is my panel coming in my house here, like you guys did with your friend Chad, here's my panel. And so what they do is they go right in here and they draw a box, and that box would be the width of the panel, the depth of that box would be 4 feet, and they hash it. If you go work in an engineering firm, you'll see it hashed like this. This means that space in the front of the panel, do not mess with it. It's a sacred cow. Thumbs up, Chad. We fully understand that one. And they make it 4. Why do they make it 4? Because if you put 4, you're covered for almost all of it. Why do they make a clearances in front of equipment? So people don't burn themselves while working energizing equipment, guys. They have enough room to run away if there's an explosion. Okay, so that's what I wanted to show. This is just about the load calculation. Okay, so I'm not going to go. We went through that one. So we talked about the clearances, Okay, so let's continue a little bit, just guys, talking about the work. Imagine all these are panels. And imagine here's a 4 feet between face to face here, if I allow 4 feet here, and allow 4 feet here, and allow 4 feet here, am I covered for almost all the conditions? Almost all the conditions except one condition. So that's what most of engineers guys do. When you start the design, they make a 4 foot. Here's my panel. So this is starting from here. This is panel 1, panel 2, panel 3, panel 4, panel 5, panel 6, panel 7, panel 8, panel 9. 9 panels. Panel 10, panel 11. All these are panels. And all of them are 1200 amps or less. You know why I said 1200 amps or less. If you put 4 feet around them, you're completely covered from all these conditions. And oh, by the way, the voltages are, let's just say these guys are 480, 277, right? These guys are 208/120, and these are 240/120. They're all 3 phase. Look at the voltages, right? So now you could have gotten on these ones 480 only. Delta. Any question, guys, about this? 4 feet around the carry, you're done. Any comments? Any questions? Do you guys understand the clearances in front of the equipment? Okay, so that's basically what I wanted to show here. The clearances, everybody got that one? Clearances is cool. Let's go now. The clearances have to allow the door to open at least 90%. Here's my door. 180 is great, but at least 90. So the door has to be able to open at least 90.
Is that in the code?
Yes.
What, do you know what code section that is?
240.20. No, where is that? It is, the clearances is 110.26. It's 110.26A2. 110.26A2. Go verify it. Okay, here's the space, guys. Keep clear, do not use for storage or sleeping. So if you want to have a nap, Brian, don't put your mattress right here and sleep there. So storing stuff, is this a violation of the code right now? Putting the stuff here? Yes. It should be removed 3 feet. You can't store things in front of it. You guys should know that because you're designers, engineers, project managers. These are the things that you need to be aware of. Okay, for electrical equipment, the way they measure them, the way they measure the feet, guys, they measure them from the box right here. So here's where your 4 feet or 3 feet comes, or from the energized parts. If it's open buses, we don't deal with open buses a lot from energized parts. So from the outside of the enclosure. Now the second thing for the clearances is, okay, here's my wall here, and here's my clearance. And this is my 3.5 foot, because this is 480/277, right? From the code. Now I want you guys to look at, how about the width? The width. The width is minimum of 30 inches or the width of the equipment. Can I have thumbs up, Chad? So if this is a panel, the width will be the width of that, right? Or 30 inches, whichever is more. So that's the width. Remember that width? It has to be 30 feet or the width of the equipment. The depth, typically what? 3.5, 4, depending on the voltage and the condition. The width is 30 inches or the width of the equipment. That's your clearance. Okay, minimum width of the equipment or 30 feet, like we said. The height, let's talk about the height of the working space. The height of the working space, it's not a big deal for Chad because he's short, but for tall people, they want the height to be at least what? Can you guys see that? 6.5. So here's a switch gear right here. I'm working, I need the width of say 6 feet, because the equipment is 6 feet, 4 feet space, and a height of 6.5 for electricians to work safely around the electrical equipment. Or the height of the equipment, whichever is bigger. If I have a switch gear, and my switch gear, guys, is 120 foot, the height has to go all the way up to the height of the switch gear. That place cannot be used other than, you can't put anything in it, because that's the working space around electric equipment. Can I have thumbs up, Chad? Okay. So we talked about the width of the equipment, or 30 inches, the height 6.5, or the height of the equipment, the depth from 3 feet all the way to 4 feet. So these are the 3 things that you guys need to know. Entrances. You have to have at least one entrance to get into, at least one entrance, sufficient area required to get access. So can you see how you have an electrical room, you have to have at least one entrance. Our entrance for this electrical is right here, right? At least one entrance. Sufficient. Oops. You got that, okay. Okay. Now here's what they're saying for large equipment, guys, only for large equipments. And large equipments defined by the code, amp I is equal, oops, why am I getting it to I equal or less 1200 amp, and width more than 6 feet. I believe that's the more than 6 feet. Did I do it right? The top one should be more, not less. Thank you. I said more, but I drew this. More, right? So the current has to be 1200 amp or more, and this is and here. And you have the equipment have to be more than 6 feet. The equipment have to be more than 6 feet, rated 1200 amp or higher, and greater than. Can I get you guys thumbs up here? If you have a B switch gear more than 6 feet and 1200 amp or more, then you have to have 2 entrances for this switch gear. You have to have 2 entrances for this switch gear. 2 entrances for a switch gear. Okay, you have 2 entrances for the switch gear in order to allow the people to escape. So if I have, here's my electrical room right here. I have 1 switch gear here, 1 switch gear here. I have to open 1 entrance here, 1 entrance here, right? 1 entrance from every side of the switch gear. So in this case, here's my switch gear. You don't want to trap people around, so you have to have different entrances for your switch gear. Let's look at the other one. Continuous and unobstructed. The exception, guys, if the door looks like this, and your switch gear, if the door looks like this, and and you orient your switch gear this way, then it just flows all the way around, right? It's unobstructed. If there's a ball of fire chasing you, you have only one way to go. If you put it right here, then you have to have 2 doors, 1 here and 1 here. Can you guys see where you're orienting the equipment require you to have different doors? So that's unobstructed. The second option, guys, is to avoid putting 2 doors. And I'm sure you guys sitting and said, who cares about 2 doors, Chad? Let me tell you about who cares about 2 doors. The second thing is to double the distance. If this is supposed to be and greater than 6 feet, if this is supposed to be 3 feet, you double it, multiply it by 2, that will make you 6 feet. Then you can only have 1 entrance. Can I have thumbs up, Chad? Doubling it. But this distance here, from here to here, cannot be less than 3 feet. Why do they care about, guys, 2 entrances for bigger equipment? They don't want you to be trapped if there is a big ball of fire coming out of the equipment. What I'm talking about, guys, here is a big deal when we design systems. So what the engineers do is they go right in the front of the equipment, guys, and they draw a box and they hash it. And they put 6 feet on it. This means do not install anything in the front of the equipment. Cool? 1200 or more than 6 feet, you need to have 2 entrances. Only 2 exceptions for this. If the switch gear is oriented where the door is straight in front of it, 1 entrance. If the switch gear, if you double the distance, if the distance is say 4, you make it 8, double the working distance. Can I have thumbs up, Chad, for the working distance and double the working distance? So that's my okay, the electrical room. So that's it, guys, in terms of the clearances. The electrical room also require a door, a panic door like this. So if this is electrical room, guys, for large equipment. Does this door qualify as a door for electrical room? No. Why? Because you have to twist. So it has to look like a panic door like this. Like EBoost doors, all EBoost doors in any building require this type. If you look at the hallways, doors in the hallways or stairways, they all require called the EBoost door. You throw yourself in them and they open. Anybody knows why? You have a big ball of fire coming out of that switch gear. Do you really have enough time to grab the handle and twist it? You just throw yourself on these bars and bam, you're out, hopefully. Okay? The last thing I want to talk, guys, about, there is a working space and there is dedicated space. Jeff, you know, and you and Darren, fully the difference. Working space is for Brian to work on the equipment. Dedicated space, guys, is for the dedicated space is to bring your conduits. Can I get you guys to understand this space, which is 6 foot, or the structural ceiling? Here's my structural ceiling, right? This space here is for me to do what? Anybody can tell me what to do here? To bring my conduits. This is for your conduits to come into the switch gear. Okay? So the smarter than Chad guys, they said right above the switch gear, or the panel, up to 6 feet or the structural ceiling, that space is sacred cow for what? For the pipes. Can I have thumbs up for dedicated space? So dedicated spaces for what? For equipment. Working spaces for what? For people. So where's the dedicated space? Right here. Look at this panel right here. From here all the way to the pit, right from this top all the way 6 feet, or the structural ceiling, you can't put any pipe other than electrical. From here all the way down to the floor, you can't put anything other than electrical. Anything other than electrical. Can I have thumbs up, Chad, to understand that? Or your pipe to come in? Okay. So that's basically your dedicated space. The last thing, guys, is lights. In an electrical room, the code requires you to have a light. And here's my question for my favorite, smartest students. Occupancy sensor. Can I do that? Can I have an occupancy sensor to control light in an electrical room? Thank you. Carrie? No. Why? Because that's changed in 2011. They said if you have an electrical room and you have to have a light, and the light have to be manually operated. So if you have an this is the only way I can wire this is to have a switch. Or the occupancy sensor have to have manual override. Manual override. You can put them in the on the auto position or an on-off position. Manual override. Can I have thumbs up, chat, for the light? Anybody knows why we need light around electrical equipment? Duh, we are working with energize. You need to be able to see it, right? Okay, here's how your panels look like, guys. You're looking at main circuit breaker here, main lugs only. We talked about the clearances. You guys remember that clearances in front of the equipment. So that's really all what I want to do about this what do you call it? This chapter. Thank you. This chapter. So let me just summarize and let you guys go. I don't want to go even to my PowerPoint presentation because really the PowerPoint is right here. Summarize. When you have a panel, they arrange the phases left to right, A, B, C. The neutral will be on the left, the ground will be on the right. In your panels, you have to label the panels with the full load current, the voltage, the interrupting current, the arc flash, the feeder that feeds the panel, and what else did we forget? And if it's a delta panel, you have to label it as a delta panel. Clearances in the front of the equipment. Right, I'm a switch gear right in the front of me, guys. You have to have from 3 feet minimum all the way to 4 feet, depending on the voltage. Or if you have a sheetrock wall or a concrete wall or another panel in front of you. So it goes from 3 all the way to 4. Cool. The depth of the working space depend upon the width. The width depend on the equipment. 30 inches or how the width of the equipment. The height, 6.5 feet, or the height of the equipment. That's a working space. Dedicated space for equipment. I'm a panel right above my head up to the structural ceiling or 6 feet, whichever comes first. That's for pipes to come right through the panel. Top and bottom to the width and the depth of the panel. So that's basically it in terms of summarizing that panel. Any comments, any questions? You can have main lugs only panel or main circuit breaker. You can have fuse panels or circuit breaker panels. What's the difference between fuse circuit breakers? Fuse are bigger, bulkier, like when Square D came here, guys. But they provide good protection though. Any comments, any questions? Any comments, any questions? I know it's Friday, so I don't want to overwhelm you. So that's basically it, guys, in terms of panel. How many circuit breakers can I put in the panel? It used to say 42, no more. You can put as many circuit breakers as you can fit. If you guys remember, it goes in multiples of 6. 6 all the way to 84 is not uncommon. What's the good design? The good design, guys, in the panel is 42 to 50. What comes? 50, 54. Is that multiple of choice? Multiple of 6 to 54. You go higher than 54. It's too many circuit breakers in one. Too many eggs in one basket. You don't want to put them.
You feed through lugs and put up the panels.
You what?
You feed through lugs and put up the panels.
Yeah. Yep. 2 panels. Any comments? Any questions? That's all what I have for you guys. Thank you. And I need to do some advising, and hopefully you guys will be able to finish the rest of your project. Thanks. Sorry.